Hi everyone, welcome to my channel. This is Divya, and in this class we are going to solve a problem on the topic basic concepts of stress and strain. So the question is: a tensile test was carried out, conducted on a mild steel bar. The following data was observed from the test. Diameter of the steel bar 3 centimeter, and in mm we can write this in mm as 30 mm, right? And gauge length of the bar equal to 20 centimeter, which is equal to 200 mm gauge length. Load at elastic limit 250 kilonewton. Extension at the load of 150 kilonewton equal to 0.21 mm. Maximum load equal to 380 kilonewton. Total extension equal to 60 mm. Diameter of rod at failure equal to 2.25 centimeter. Determine Young's modulus, the stress at elastic limit, the percentage elongation, the percentage decrease in area. So, tensile test is conducted. From this question we can say that a tensile test was carried out for a mild steel bar, and the diameter of the bar is 30 mm, gauge length of the bar is 200 mm, and the load at elastic limit. The elastic limit of the material is 250 kilonewton, and the extension observed at 150 kilonewton equal to 0.21 mm, maximum load equal to 380 kilonewton, total extension equal to 60 mm. Diameter of the rod at the time of failure equal to 2.25 centimeter, which is equal to 22.5 millimeter. 22.5 millimeter. Okay, so this is the diameter at the failure is also called as neck diameter, right? Okay, so first thing we need to find out is Young's modulus. We need to calculate Young's modulus of the material. So let us just find out Young's modulus. So Young's modulus can be defined as the ratio of stress to the strain. Stress can be tensile stress or compressive stress. To the strain. So Young's modulus can be referred as the ratio of stress to the strain. So the stress can be tensile stress or compressive stress, and then corresponding strain, right? Corresponding strain is tensile. If a tensile stress is taken into account, then the stress produced is tensile strain. Strain produced is tensile strain. If the stress is compressive stress, then the corresponding strain is compressive strain. So E equal to tensile stress or compressive stress to the tensile strain or compressive strain. Okay, so we need to have, so this is the tensile stress. So E value is sigma tensile stress to the tensile strain. So stress can be represented by the symbol sigma and strain can be represented by the symbol E. So first we need to have sigma value. Sigma is load per unit area. We can calculate have the load as 150 kilonewton because the Young's modulus value should be found out within the load for the load value within elastic limit. So elastic limit is 250 kilonewton, which is given in the question. So we have to consider a load which is below 250 kilonewton. So I am considering this 150 kilonewton, right? So load is 150 kilonewton. So 150 into 10 power 3 Newton, right? And area is equal to cross sectional diameter of the cross sectional area of the circular rod is pi by 4 into d square, right? D represents diameter, so diameter is 30 square, right? So you need to calculate the value for this. So 150 kilonewton, right? 150 into 10 power 3 divided by pi into 30 square divided by 4. So the load value is stress value is 212.21 212.21 Newton per mm square. Newton per mm square. right? And we need to have this strain value. How can we calculate strain value? Strain is defined as the ratio of change in length to the original length, right? Change in length divided by original length or gauge length. You can take, you can consider gauge length for this question, right? So change in length for 150 kilonewton load, change in length is 0.21 mm, right? So change in length is 0.21 mm divided by original length வந்து 2, it is 200 mm, right? So we have to take the ratio between 0.21 to 200. So strain value is 1.05 into 10 power minus 3 into 10 power minus 3. So now we know stress value and strain value. From this we can calculate Young's modulus value. So Young's modulus E is equal to sigma stress divided by strain, right? Stress is 212.21 Newton per millimeter square divided by strain value is 1.05 into 10 power minus 3. So stress value is Newton per mm square, unit of stresses, and the strain is unitless parameter. Now if you take ratio between these two, 212.21 divided by 1.05 into 10 power minus 3, you will get 2.02 into 10 power 5 Newton per millimeter square. So this is Young's modulus value. So Young's modulus of the material have been found out. So next parameter you need to calculate is the stress at elastic limit, right? So next thing you need to calculate is stress at elastic limit. Right? Okay, let us calculate stress at elastic limit. So elastic limit is the stress value which is stress is at elastic limit. As usual, stress formula is load divided by area. Load at elastic limit is, what is the load at elastic limit? It is given in the question itself. It is 250 kilonewton, right? Okay, now stress at elastic limit, load 250 kilonewton. So 250 into 10 power 3 Newton, right? And the area is as usual pi by 4 into original area, original cross section, right? So into d square, diameter of the rod is 30 mm, so 30 mm square, so mm square. So if you take relation between these two values, 250,000 divided by pi into 30 square. So your stress at elastic limit value is 353.68 Newton per millimeter square, right? And the third subdivision you need to calculate is percentage elongation. So the formula for percentage elongation is original length, final length minus original length, or initial length. We can consider that as initial length, right? Whole divided by initial length into 100. right? So what is the final length? So before elongation, what is the initial gauge length of the bar is 200 mm. So this 200 mm is initial length of the bar. So what is the final length? Diameter at the time of failure. So the total extension it is given. The total extension is 60 mm. So initial length plus extension will give you final length, right? So final length, initial length is 200 mm and the final extension at the time of failure is 60 mm. So final length is 260 mm. So initial length again 200 mm divided by 200 into 100. On simplifying this, you will get 60 divided by 2, which is equal to into 100, which is equal to 30%. So 30% is the percentage elongation for this material, for this loading condition. Right? So next you need to calculate, next parameter you need to calculate is the percentage decrease in area. So at the time of failure, what happened? The diameter of the length of the material has been increased and the diameter of the material is decreased. At the time of failure, there is some rupture happens or fracture happens at neck diameter. So the neck diameter is 22.5 mm and initial diameter is 30 mm, right? So percentage decrease in area. The formula to calculate is equal to initial area minus neck area whole divided by initial area into 100%, right? So the initial area value is pi by 4 into diameter square. Diameter is 30 square, right? Initial diameter 30. At the time of failure, the diameter is 22.5. So that is neck diameter, right? So 22.5 divided by initial area pi by 4 into 30 square into 100. So we have to simplify this one and find out the percentage decrease in area, right? Okay, so we can take the pi by 4 out of this equation. So you will get pi by 4. Remaining you will have 30 square minus 22.5 square whole divided by pi by 4 into 30 square. 30 square into 100. So this pi by 4, this pi by 4 can be cancelled, right? So 30 square minus 22.5 square whole divided by 30 square multiplied by 100. So you will get 43.75% is the decrease in area. Right? So we have calculated all the parameters which are needed. Right? So Young's modulus, stresses elastic limit, percentage elongation, percentage decrease in area. So if you have any doubts in this question, please comment. So I will refer and try to clarify your doubts. Thank you. We will meet on the next video. Bye bye.